Okay, and we'll look at the next problem. This problem wants us to find R Thevenin and V Thevenin. So we notice here we've got this interesting thing called RL, uh, and it looks like that R of L is connected already. Interesting, right? Well, uh, this is what we call a load resistor. Okay, so whereas before we just had that imaginary wire, same concept, but now um, this is what we're going to be evaluating later on. So if we take a look at this problem, we see we have a load resistor. What we're going to do is that we're just going to say, okay, we know that that load resistor is there and that it exists, but for the purposes of our analysis right now, we're just going to do what we've been doing, so VOC, okay? And we're going to come back to that later, the load resistance later. Okay, so if we want to find V Thevenin and R Thevenin, we're just going to crank out our steps. So step number one is going to be determine any dependent sources. I see none, so we're good. Step two, we're going to now zero out our sources. So we only have a battery here. It's another way to draw a battery. So plus minus, same way of saying like that, that's just a battery as well. So that will turn into just a wire. And we will come down here and redraw it. R1, R2, and R3. And this is R4. That's A and that's B. Okay. And if we came down here, imaginary source, plus minus. Okay. Um, now what we need to do is step three, find R Thevenin. So looking here, we've got a couple things we can do. First step is we see series one. Those R1 and I'm sorry, R2 and R3 are going to be in series. So all right, R series one will be R2 plus R3. That'll be equal to 47 plus 22. So it'll give us 69 ohms. And then we see that after we combine R2 and R3, that these two are going to be in parallel. I'll call that parallel 1. So R parallel 1 is going to be equal to R series 1 times R1 over R series 1 plus R1. So that'll be 69 times 100 over 69 plus 100. And what will that give us? That'll give us 40.8 ohms. Okay, so let me redraw it one more time. This is A, B, resistor 4, and this is R parallel 1, and VOC plus minus. Okay, so then now we see that the final two here are in series. So series 2. So R series 2 will be R4 plus R parallel 1, which will be 140.8 ohms. Then finally, if we drew it out one last time, R series 2 VOC plus minus. We see we have one resistor left, so our equivalent is equal to 140.8 ohms. Therefore, our R Thevenin is equal to 140.8 ohms. All right. So now we need to find VThev. So we'll jump back to step 4, and we'll go back to OG circuits, which will just be that. Here, let me just go ahead and waste everyone's time. R2, R3, R4. That's A, that's B. This is 10 volts, and this is R1. Okay, and then plus minus VOC. All right, so if we look, we see that we're going to have our branches in parallel for this VOC. So that VOC is in parallel with that branch. So if we find the voltage from here to there, we can say that that's going to be equal to VOC. So I'll call that V23. Yeah, that'll work. All right. And if we looked at the current that's running through the circuit here, it'll pass through that 1 ohm or that R1. It's going to bypass the A branch because it's an open wire. It'll pass down through here. It'll bypass the B wire because it's open, and then it'll loop back around and continue that way. So in reality, this is another way of writing it out. This is R2, R3, R1, and then 10 volts. And remember, we're trying to find voltage from here to there. And we see that's in series. So therefore, we can do a voltage division on it. And if we want to find V23, that would just be resistance 23 over R series times 10 volts, where R23 is just equal to R2 plus R3, which will give us 69 ohms. So V23 is going to be equal to 69 over R1 is 100 plus 47 plus 22 times 10 volts. So V23 is going to be equal to 100. This will be equal to 4.08 volts. And like we said, V23 is equal to VOC, which is equal to V Thevenin. So therefore, V Thevenin is equal to 4.08 volts. So you might be asking, well, that's great, Jordan. What about that load resistor? We didn't do anything with it. And that's right, we didn't do anything with it. Um, the reason being is because that's supposed to come at the very end where we are doing our actual Thevenin analysis. Okay, so if we were to go and build our Thevenin circuit, so where VThev is equal to 4.08 volts, where R Thevenin is equal to, oh gosh, whatever it was, 140.8 ohms, and we had those terminals plus minus VOC. So whereas before we were saying that, okay, we're just going to act like there's an imaginary wire, but now with a load resistor, we say, okay, at the very end, we're going to come in and drop a load resistor. And whatever that load resistor was like 1 kilo ohm. So 1 kilo ohm. And the idea behind this is what the Thevenin circuit actually does is allow us to take this load resistor and then change it out. So we can change it out to be, a 500 ohm resistor, or we can make it to be a 10 ohm resistor, or we can make it to be a 1 ohm resistor. Whatever we want it to be, what it does is it creates a circuit that allows us to do analysis much quicker. So let's say, for example, we wanted to find the current through the load resistance in a regular circuit. We would now have to do we'd have to break it down and find an equivalent resistor, and then we would have to do a current division or a voltage division, and then we'd have to do Ohm's law. And that might not be too bad for one problem, for one resistor. But what if we go and change the load resistance out? Well, then you've got to do that whole analysis again. And it's cumbersome to keep repeating the same process over and over again. So the Thevenin and Norton circuits basically say that, you know what, I don't want to keep doing that analysis over again. Let me just create a simplified circuit that if I want to change the load resistance, I only have to do one step of work to find the new value. So now I only have to do one line of algebra to figure out what the current is through it or the voltage is through it. And so it can't be a very powerful tool when applied in the correct scenarios. But just a little bit of background, I'll see